As we have motivated in the previous lecture, I have good news and bad news. Good news is that finally we will understand what does the composition of a function look like, and in the exercise classes we will do some computations supported by SageMath or Magma, and finally we will see that the abstract concept we have seen in a more concrete way. But the bad news is that we have to give some formal definitions, and the first definition which is called the divisors of F, or more formally, we will introduce a spatial group structure inside of the function field that will be called the divisor group of F. Briefly, we denote it by div of F as the free abelian group with respect to an addition. We will define it soon. Generated by the places in the function field F. That means this divisor group contains the sum of the integers, sum of the places with integer coefficients, with almost all coefficients 0, or equivalently we can say that only finitely many coefficients, non-zero coefficients, and such an element is called a divisor in the divisor group of F. As a two example of a divisor, let me consider the rational function field, and the divisor, which is defined as px plus p infinity minus 2px minus a, will be example for the divisor because it contains the places, like a kind of set of places with only finitely many non-zero coefficients. And regarding these non-zero coefficients, we will introduce what's called the support of A, which is denoted by sup of A briefly. It contains the places with non-zero coefficients that appears in the sum of the divisor. For instance, if you consider this first example, if you consider the divisor in the first example, its support will be a finite set, contains the places px, p infinity, and px minus a. And in particular, actually, we also consider the all places as a divisor. And in this case, it will have a spatial name as prime divisor. And thanks to this definition, in it we can see the set of places as a subset of the divisor group. So we say that this is a group, and with respect to a component-wise addition, for instance, in the again rational function field, if you consider two divisors A1 and A2, we will perform the addition by checking their components with respect to each places that appears in their sum. For instance, we have only px in the first divisor and we don't have px in the second divisor, so that means, or this is 0 times px. 1 plus 0 gives us 1 times px. And for the p infinity, as a component-wise addition, we see that minus 3 plus 1 gives us minus 2. And we can also add this 2 places, and sum of the coefficients gives us sum of the places. And with respect to this component-wise addition, we can define the addition in the divisor. And with respect to same operation, we can introduce its 0 element, and we will call it 0 divisor. This is a divisor with all coefficients are 0. And with respect to this 0 element, we introduce the additive inverse of a divisor by multiplying coefficients by minus 1. And in addition to its their group structure, we will also endow it with a partial order. In other words, we can compare 2 divisors by checking their integer coefficients at each component. Or we can also consider one divisor is strictly less than the other one if their coefficients satisfy this inequality at each place. For instance, again, in the rational function field, if we consider the place A1 and the place A2, here A and B denotes different non-zero constants, then in this case, we can see that A1 is bigger than or equal to A2 by comparing each coefficients that appears in the sum, because 1 is bigger than or equal to 0, 1 is bigger than or equal to minus 1, 2 is bigger than 0, and here 0 is bigger than minus 2. But it's not always possible to consider 2 divisors. For instance, in this case, for the divisors B1 and B2, which is defined as the sum, neither B1 nor B2 is bigger than or equal to the other one, because for this inclusion, it's enough to check that the coefficients of the places x minus a doesn't satisfy this inequality. And similarly, we see that the coefficients of the place p infinity doesn't satisfy this inequality. So this is why b0 or b2 is not bigger than or equal to, or less than or equal to the other one. And with respect to this partial order, if a divisor has always positive coefficients, we call it a positive divisor. Or in the literature, you can also see the keyword effective. We will explain it why it's called effective later when we see the Riemann row spaces. And again, depending on their sum. If you consider the discrete valuation maps component-wise, we can introduce the valuation of a divisor A. More explicitly, for instance, again in the rational function field, for the place A, its valuation at x, this is corresponding valuation to place Px, is 1 because it has coefficient 1. But valuation at infinity of A is 1 because the coefficient of the P infinity in the sum is 1. And finally, for the valuation Vx minus A that corresponds to place Px minus A gives us -2 because it has coefficient -2 in the sum. And for any other irreducible polynomial, which is different from the linear factors x and x minus A, the valuation of A will be 0 because such a irreducible polynomial does not appear in the sum with non-zero coefficients. And depending on the degrees on the places in their representations of a divisor, we will introduce the degree of a divisor as a product of the non-zero coefficients and the component-wise degree of the places. This is obviously an integer, and we can view this degree as a homomorphism between the divisor group F and the integers, which is written additively as a group homomorphism, because the degree of the sum of two divisors can be defined the sum of the degree of each divisor.